It's my great pleasure to speaking with you this evening. I'm from Department of Material Science and Engineering. Can everybody hear me? Okay, good. So
scream a little bit because the acoustics aren't here.
Okay, I will try to raise my voice. So I'm Guodan. I'm from Department of Material Science and Engineering from University of Michigan. Today, I'm going to talk about my research work on engineering and designing new organic donor materials for high-efficiency solar energy application. Organic materials, as name indicates, they are organic materials, but they are softer materials. These organic materials, but they conduct electricity. Because of they conduct electricity, we use these organic materials in our solar cells. Solar cells, as many of you already know, is devices that convert sunlight into electricity. So this is a green energy harvesting process. And solar energy nowadays have proven to be one of the renewable energy sources for our ordinary life application. So in my talk, first I will introduce, we are talking about solar cell. So I'm going to introduce what is the solar energy. Then why we pick up organic materials. Now we pick up organic materials, how do we build up solar cells using these organic materials? Also, then I will introduce what kind of new materials we are using now for high efficiency solar cell application. Then I will give a brief conclusion. So solar energy, as many of you know, is a green energy process. And why we pick up solar energy for a research topic, there are many of reasons. One of the reasons is the energy consumption. In USA, people estimate there are 5% of global population, but they consume 22% of global energy consumption. This is a really large number. Where does this energy come from? This energy, 86% of this energy comes from the burning fossil fuels, burning of petroleum, burning of the natural gas, burning of the coal. During this burning process, yes, they are generating energy, but at the same time, they are generating pollutions. They are generating carbon dioxide, which has a greenhouse effect. They are generating nitric oxide or sulfur oxide, which has the problem of acid rain. So they are generating the pollutants, which affects the planet we are living. So, but in contrast, for the renewable energy like solar, wind, wood waste, they occupy less than 1% of the energy consumption. So, what we are going to do when we look out the New Hampshire, look out the USA, look out on the Earth, there are a tremendous amount of energy, solar energy available that's illuminating our Earth. It is around 10 to 24 joules. So in reality, we have a bunch of solar energy available for us to use, but we haven't used it. Because the global energy consumption on the Earth is 10 to 20 joule. So in comparison, two numbers are really two large numbers. Let me break it down further. So if we can efficiently collect all the solar energy that are illuminating our Earth for 1 hour, this amount of energy we are collecting can power our human activities for 1 year. So 1 hour, 1 year. Yeah, that's cool. Solar energy is really cool. But we haven't did too much work in this field. And even when we look at the USA, so we are talking about solar energy, we are talking about solar devices. So say we have 10% solar cells, and it needs 1.7% of the land to power the energy consumption in USA. And this amount of area is this square. It's like 230 times 230 square miles. Just So this is there's huge energy waiting for us to utilize. So what is solar energy? Let's look at the solar spectrum. And we know that in the solar spectrum, there's a broad wavelength. It includes UV light, it includes visible, and it also includes the infrared. For the infrared, we know infrared is accumulation of sunlight. Basically, it gives us heat, keeps us warm. Actually, it gives us the summers. So, but for the UV light, visible light from 400 to 700 nanometer, there's a tremendous photon flux here. For the solar application, we are typically focused on the visible light and the infrared light. So, and if we integrate the solar spectrum throughout the wavelength region, this typically called the one-sun illumination is 1,000 watt per square centimeter. And this is a number we typically compare the efficiency between different solar cells. Like silicon, polycrystal silicon, they have efficiency like 10 to 12%. Usually people measure it at a standard one-sun illumination. But so then question still remains why we haven't used solar energy a lot in our ordinary life. The biggest problem is the cost of the solar energy. When we compare the solar electricity with the coal, gas, wind, nuclear, you see the solar electricity costs a lot. So right now for the real application, we have to bring down the cost of the solar electricity, make it comparable with the other energy sources. Things are getting much better. Right now, in some areas, like France, they have solar electricity costs less than the other energy sources. They have a broad application. It was estimated like in 2010, the solar electricity cost is 20 cents per kilowatt 1 hour. And if things still goes on much better, like efficiency goes up in 5 years, like 2015, it will have a chance for the solar energy, the cost of the solar energy goes down to 10 cents per kilowatt an hour. Once we get that range, the solar electricity, the cost of the solar electricity will be compatible with other electricity sources from coal, gas, wind, nuclear. So what we are working on to improve the efficiency, then search for alternative materials that have the low cost. That's why we focus on the organic materials. Organic materials, they are softer materials and they are inexpensive. We think about this, what will be cheaper than a plastic material? And another thing for the organic materials is they have the ability, they have the potential for the low cost of fabrication. We know organic materials have some organic material have very good solubility in the solvent. Then we can use very convenient thin film fabrication, like low-to-low fabrication methods. So in combination with the low cost of materials and the fabrication of the thin film, organic electronics has huge chance for the low cost of production. Also, another attractive thing for the organic materials is chemical versatility. You see, the color of the organic materials can be tuned, make the wood very colorful. Also, we are producing thin film organic electronics, and they can deposit into a variety of different substrates like plastic, metal foils, glass, so they are lightweight in compared with the silicon cell. Also, they can be flexible. So nowadays, when we go back to the research field here, the organic photovoltaics in like 20 years ago, in the whole solar cell field, it only have 5% research reports. But after 20 years, the reports on the organic fields ramps up quickly. So this is, it will be in the academia field that job to further improve the efficiency to make the solar organic PV efficiency comparable to the inorganic solar cell. At the same time, as we know, the cost of solar cell, the production of the solar cell, the packaging of the solar cell costs a lot. So it will always also involve efforts in the industry to bring up a large-scale production of the solar cell. Then the efforts in academia and efforts in the industry build up together to reach the goal for the high-efficiency, low-cost solar cells. So how does a solar cell work? The left image basically shows how to generate electricity. The typical organic solar cell is illuminated by one sun illumination, and we can see the power generated here. In terms of how do we measure the solar cell efficiency, the left light image shows the IV measurement. Actually, the fourth quadrant of this figure is where the power generated. At 0 voltage, we get a photocurrent. But at this point, it doesn't generate power. As we know, the power is produced of photocurrent and the voltage. At this point, voltage is 0, so this power is 0. But as we go through these curves here, the solar cell is generating power until it hits the maximum point. And this is where we calculate the power conversion efficiency. The maximum power generated by the cell divided by the illuminated power intensity, we get efficiency. And then as we go through this curve, go on until the photocurrent hits up a 0 point. At this point, this is the maximum voltage this cell can generate. We call it an open circuit voltage. And also, we want this curve as square as possible, to generate much power. So we have another parameter, field factor, to characterize the box-like curves. A field factor is defined as the maximum power generated divided by the product of photocurrent and the VOC. So J sub S, short circuit current, VOC, field factor, these three parameters actually determine the final efficiency. So to build up high efficiency solar cell, we have to consider these three parameters. What is organic solar cell? Organic solar cell, the biggest difference from the organic solar cell and inorganic solar cell is that the absorption of one photon in the organic solar cell, it generates one exciton. This exciton is strongly bonded electron-hole pair. So at that moment, electron-hole pair is not free. But in contrast for the silicon inorganic solar cell, the absorption of one photon actually generates free electron-hole. So how do we, for the organic electronics, how do we dissociate the exciton? It involves the interface. This interface between the donor acceptor has to be energetically favorable for the exciton to dissociate into free electron here and free hole here. At this point, this material actually donates electron to this layer. So this layer called acceptor, and this layer called donor, and this layer called acceptor. So typically, organic solar cell, it has two parts, donor and acceptor. In terms of the photocurrent generation, there are 4 sequential steps. The first step is the light absorption. It generates exciton. Then exciton diffuse into the interface between donor and acceptor. Then once the exciton see an energetically favorable interface here, it will dissociate into free electron hole pair. At that time, the electron hole pair will be collected by the electrodes effectively. So for the generation of the photocurrent, the 4 steps determine the final photocurrent generation. When we integrate the efficiency from the 4 steps, we get external content efficiency. Its content efficiency is the internal quality of the device structure. Basically, it tells the probability for one photon to generate one electron hole. And this EQE number is wavelength dependent. When we integrate EQE with the solar spectra I just showed before, we can get the photocurrent. So now we know the mechanism of the organic solar cell. How do we build up an organic solar cell? Typically, there are 2 device structure. The first one is called a planar junction solar cell. The second device structure is a bulk junction solar cell. As I just mentioned, organic solar cells involve interface to dissociate electron hole pairs. So in these 2 structures, it also creates interface. For the planar, it creates continuous interface here. But for the bulk junction, it creates a lot of interface throughout the layers. There's advantage of this structure here because once electron holes are generated in the donor acceptor, they have very continuous transport paths to electrons. But this structure has one limitation. It has only one interface, continuous interface. That's limited the photocurrent. In contrast, for the bulk solar cell, donor acceptor are intermixed throughout the whole layers. So there are interface everywhere. That's good for the exciton dissociation. But this intermixture of donor and acceptor is in a disordered. It's disordered. So at the other hand, it lost the continuity of each material. So the extraction of electron and the hole pair will be a big problem in this structure. Then, when I take this project, I face 2 challenges. I need to maximize the interface for efficient exciton generation between donor, efficient exciton dissociation between the donor and acceptor. Also, at the same time, I need a continuous transport paths for electron hole pair. What I'm going to do, so in my research work, I'm trying to take the advantage of these 2 structures, but I'm trying to solve their limitation. So what I do is I dissolve my organic material in solution and spin cast on top of the substrates. Then I apply thermal annealing process to change its morphology and crystallinity. Because the S-cast thin film, there are also some residue of the organic solvent. This residue organic solvent will evaporate during the thermal annealing process. Because organic solvent evaporates, it also helps reorganization of the organic materials on the thin film. So we see morphology. We see very obvious morphology change here. This is S-cast AFN thin film of the organic materials, organic thin film. This is amorphous and it's very rough. Its roughness is around 0.7 nanometer. After we apply the thermal annealing, the roughness of the thin film doubles. And the selected area diffraction pattern also. Guys can see the rings here, but this selective diffraction pattern characterization shows is polycrystal. So we see a huge change. We simply apply the thermal annealing, but we change the crystallinity of the thin film. It evolves from amorphous to polycrystalline. Then when we look at this image, we have the interface. We have enough interface for the exciton dissociation. At the same time, we have a continuous transport path for the hole and electron. So the other layer, the acceptor layer, we still apply the thermal evaporation to finish the device growth. So that's the basic idea for the device structure design. Then we have to make a comparison between these three structures to see which device behaves the best. So I made three devices. The first device, a planar cell, donor, squaring, and the C60 are thermally evaporated. They create a planar junction. This squaring PCBN device, they are spin cast from solution. So squaring PCBN basically is a derivative of C60, just makes C60 soluble in a typical organic solvent. Then we spin cast the thin film on the ITO electrodes. The third device I'm making the squaring C6 nanocrystalline cell. So as I said, we spin cast a thin film of squaring donor material and apply the thermal annealing. Then we use thermal evaporation to deposit the C60 on top of it. We create a squaring C6 nanocrystalline structure. And the left image shows the IV measurement of the three devices. So as I just mentioned, if you want the maximum efficiency, you want the IV current voltage curve, the most box-like. So we can see the nanocrystalline cell have the most box-like IV curves. And it also has a maximum photocurrent. And when we look at the EQE response in this figure here, we can see the nanocrystalline squaring C60 cell has a broadened photon response, and it ranges from 300 nanometer to 800 nanometer. So we now know squaring C60 nanocrystalline cell has a best performance, and the efficiency is around 4.4%. The then question remains: can we move up the efficiency further? Can we further increase the photocurrent? Can we further increase the open circuit voltage? Can we further improve the fill factor? So what we do is we try to engineering the donor materials. We want these donor materials have broadened the spectrum. We want this material have longer wavelength absorption, and we want this material itself has a broadened coverage of solar spectrum. So what we do, we focus on the material design. This is the original material we are working on. It's called squaring. We call it squaring because there's a squaric functional group in these molecules. And this is the backbone of these molecules. And we attach symmetric alkyne functional groups to the nitrogen. Now we want to tune this original squaring material. This is a parent material. How do we do this? We substitute this alkyl function groups with phenyl and naphthalene function groups. We choose these functional groups because this groups has strong electron withdrawing function that will tune the absorption spectrum of the parent squaring. This is 4 new materials we are working on now. The most interesting here, when we also make the parent squaring asymmetric. Then we can tune the absorption spectrum of the parent squaring to the UV light. So the spectrum of DPASQ is around 400 nanometer to 650 nanometer. It fills the gap between the absorption of C60 and the green light, the red light absorption. When we take a look at the color in the solution. DPASQ, it absorbs the green light region. It appears as a red. And this squaring 1 MPSQ, DPSQ, it absorbs at red light region. So it appears as greenish. So how do these 4 new materials behave in the real device performance? So we put all 4 new materials in the device structure. We spin cast the thin film of the squaring materials on top of the ITO substrate. Then we do the thermal evaporation of C60 and BCP. Silver is as a metal contact to finish device growth. And actually, we are doing a pretty good job for all these 4 materials. The efficiency is between 3.6% to 4.3%. And because we have a strong electron withdrawing groups attaching to the parent squaring backbone, so we can tune the energy level of the donors and make the energy offset between the donor and acceptor more favorable for the exciton dissociation. It also increases the interfacial gap between the donor and acceptor. So in this way, we can improve the open circuit voltage. So it improves from 0.79 volts to 0.99 volts, which is close to 1 volt. And the fill factor of DPSQ C60 solar cell actually reached up to 0.74, which is very close to the silicon cell. Silicon cell, the fill factor is typically around 0.8. So we are doing pretty good job in terms of the engineering these new materials to our device structures. Then we still want the efficiency to be much higher, and we know how to do it. As I just mentioned, we know we can use the thermal annealing process to change the thin film morphology and change the thin film crystallinity. So we apply the same strategy on this device, 1 MPSQ C60. And we can see in this, the left figure shows the external contact efficiency versus wavelengths. For the annealed 19C degree annealed 1 MPSQ device, the EQE response improves from 29% to 32%, and the EQE responsivity from C60 improves from 42% close to 46%. So with the 19C annealed device, we have seen much better solar spectrum coverage. Light image shows the efficiency versus power intensity of those 1 MPSQ C60 devices. So we can see the power intensity. You can look at the power intensity as like different weather condition. The lower power intensity can represent a raining or windy day, and this large power intensity can be looked at as like sunny day. So, but in terms of the weather change or the different power intensity change, our device has a very stable performance. The efficiencies range around 6% to 6.4%. Actually, at the 0.2 sun, we get 6.4%, which has been one of the highest efficiencies in terms of the organic solar cell. So we are doing a good job. in terms of the efficiency. But some of you may ask, you said you have a very broadened solar spectrum coverage from like 300 nanometer to 800 nanometer. How about this part? There's gap between the donor and acceptor here. So what are we are still losing the photons in this area. What are we going to do? How do we do further to fill this gap and improve the photon harvest? So what we do, we use the branding. Now we have material. We have green solution here, 1 MPSQ. We have a red solution, DPASQ. It absorbs this region with wavelengths from 40 nanometer to 600 nanometer. Actually, we can see DPASQ actually fills the gap between the C60 absorption and the 1 MPSQ absorption. So we do have one material available now that can fill the gap between the absorption of C60 and absorption of the 1 MPSQ. What are we going to do? What we do is we mix this solution, two solutions together, and in 1-to-1 ratio. Then we have a blended solution. That's most interesting. The color changes. It's a purple color. So this solution can absorb red light. It absorbs green light, and it appears a purple color. So how about the device performance? We can see the blending cell is really doing a good job in terms of fill the gap between the C60 and the squarine materials. So this is one way we are working right now to fill the gap between the absorption of donor and acceptor to move up the photocurrent generation. Let's go back, look at the fill factor again. As I just mentioned, we have a fill factor as high as 0.74. The question is, are we reaching the maximum number we are going to reach? Then we do a simple calculation of the IV curves. So before we do this, let me introduce a brief circuit of a solar cell. For solar cell, we can regard solar cell as a stable photocurrent source, and in parallel with a diode. And this diode is connected with two resistors, a series resistance, a parallel resistance. So even with them, we can see even without the photocurrent generation, the solar cell is a diode, but it also has some internal resistance. The internal resistance typically is due to the carrier mobilities, the contact resistance, and so for any solar cells, the fill factor cannot be reached 1 because it has internal resistance. Even for silicon gallium arsenide, the fill factor can never reach to 1. So let's look at my organic solar cell. This is a IV current voltage at dark. In dark, this is typical. It shows the typical diode behavior. So suppose we are generating the photocurrent at a one-side illumination, and we shift the curves in the dark to this position, and this will be the most idealized IV curves I'm going to generate from my diodes. So then we do the calculation of this curve, and the fill factor is 0.78. So this means your solar cell, you test the solar cell without illumination, and then you test the solar cell under illumination. The best number of the fill factor you can get is 0.78. Suppose we don't have any other recombination happening in our devices, And our measured data is 0.74. So we are really doing very good job in terms of the resistance control in our organic solar cell. And that we don't introduce extra resistance to our solar cell. So our number 0.74 is pretty close to the idealized number 0.78, or the number calculated based on the Shockley circuits theory. So overall, we have proposed and designed a unique nanocrystalline organic solar cell structure. We also have synthesized new organic materials to build up the high-efficiency solar cell, and at one sum illumination, our solar cell can reach up efficiency as high as 6%. We are still working on the blending cell. We are still working on the new material synthesis to further improve our device performance, and we want to reach up efficiency as high as 10%. Then we will go to the next stage to commercialize our solar cells. As I want to thank my advisor, Stephen Forrest, and our collaborator, Professor Thompson, USC, and also my colleagues in our group. I also want to appreciate financial support from Air Force Center for Solar and Thermal Energy Conversion at UMich and GPAC. Thank you all for your attention.
Excellent. Thank you for a wonderful talk and for being on time. Awesome.
Thank you.
Other questions? Yeah.
When you mix the two organic materials that have absorptions at different wavelengths, are their voltages different? Do you lose some efficiency because the voltage is different?
The voltage actually are very much similar. Let me go back to my slides. So I'm blending 1 amperes-Q DPASQ material together. The voltage of this material is 0.9 volts. The voltage of DPASQ close to 1 volt. So when we are blending these two materials together, we gain photocurrent. But at the same time, we don't lose too much for VOC. VOC is between these two values, is around 0.92 volts. At the same time, these two are good material. The fill factor is around 0.74. This is so we will take advantage of these two new materials. We want these two materials contribute to photocurrent. At the same time, we don't want lose the VOC and the fill factor. So this gives us a huge chance to improve the photon response throughout the whole wavelength region. As here, we have this material, we have this material, we have this material. So we can see our solar cell have broadened the spectrum coverage, ranging from 300 nanometer to 800 nanometer. Actually, it's 820 to 20 nanometer. So this is one of the direction we are working on now to want to ramp up the efficiency from 6%, even higher, like 8 to 10%.
Is it surprising that your open circuit voltage is not just the lower of the two? You said it's actually in between them?
It's really surprising. And when I first thank you for asking this. It's really surprising. When I first get this blending cell performance, it surprised all of us, my advisor and our other students. We make this material together. Actually, it doesn't affect the VOC and the fill factor. So that's why it gives us huge chance. One of the reasons is because their energy level, the energy level of the DPASQ and the 1 MPSQ, we call the HUMO level, the highest occupied level here, 5.3, 5.4. They are well aligned. So they have comparable energetic level, and we can put them together. So at the same time, we can generate more photocurrent from these branding cells. This really gives us a huge chance in terms of the efficiency improvement.
Maybe a quick sense maybe of the big picture of where organic semiconductors are in the commercial space? Do they exist at all today? Are there companies producing them in mass quantities?
They do exist. Yeah. Think about, I know OLED cell phones already available in the markets. And I know Samsung company in Korea, they have a separate division to dedicate on the large scale organic display application. They estimate they will have product at the end of this year for the flexible OLED displays. And
those operate with like 3% efficiency?
They are working on the organic lighting emitter diodes. But they are using organic materials, but they are in the limiting diodes application, not a solar cell. In terms of organic solar cell, I know Kanaka company in Boston, they have some commercial product of solar panels on the backpacks. They have the low-to-low fabrication facilities for the large scale fabrication of solar panels. They do have. So. I know Applied Materials. Applied Company. They have new facilities to produce large-scale OLED organic lighting emitter diodes. So they are very good supply for the large-scale facility. So, yeah, organic materials so far they do have some products in the market, but in terms of the organic solar cell, as I just mentioned, the efficiency is not as high as the inorganic solar cell. So that's why it's on the research part. It's in the academia. In the academia, we need to put more efforts on this area to ramp up the efficiency to larger than 10%. Once we at that stage, we will have a similar application like OLED. Organic lighting emitter diodes. So,
what you were just saying is very close to the question I wanted to ask of how high does the efficiency have to get for it to be attractive in different applications? So you're saying 10% is a threshold where it would be start to be used in some applications. What kinds of applications would those be, and how high would the efficiency have to be to get into the mainstream?
Okay, that's a good point.
Connected solar power.
Yeah, some people have done the calculation in terms of the efficiency and the final product. So, because for the real application, we have to lower the cost. Lower cost, we have to improve the efficiency. So they have the limit of 10% efficiency. We have to have 10% efficiency. Then they do the calculation of the cost. So. Based on that calculation, we have 10% cell. Then we will have large scale fabrication technique available. Then that calculation is like the cost of the solar panel will be around 20 cents per kilowatt an hour. Once we enter that stage, the solar electricity is comparable to other sources of the energy electricity. Then we'll have application like in the solar cars and solar powered house, also cell phones, backpacks, and even windows. So we can assemble our cell to the windows. There are a lot of opportunities for the high efficiency, low cost solar cell application.
One last question.
Yeah.
So I have a question about this OLED efficiency versus solar cell, because I think OLED probably has better efficiency than solar cell because you're focusing on one wavelength. But the display probably want to apply in different
think this is two different areas. For OLED, they looking for the light emission efficiency. So basically, the input is the power from the electricity. So the output is the colors or the light intensity. And for solar cell, the input is sunlight. The output is the power. So it's quite different. So in terms of the efficiency of the OLED, right now in the lab, they can reach like 30% external content efficiency. And for our organic PV, so I did the best one for this cell, we can get 46% in terms of the external content efficiency. And they are pretty comparable so far. But also one advantage for application for the OLED is can be flexible. Also, it's a full color, and you can view the OLED display in a different angle without changing too much of the contrast. So that's one of the advantages of the OLED display. So but in terms of the efficiency, there's no direct comparison between the OLED and the organic PV because they are running pretty much very different mechanisms. And for the power conversion efficiency for the OLED right now, I think it's still around 10% region.
What about photodegradation? How long do these last in sunlight?
That's a really good point. So, really good point because first of all, my question to your answer, like the photo degradation, our organic solar cell is unknown because we haven't set up a complicated facility to test it. It involves packaging of our device and continuous illumination of our sunlight. So it needs we need to apply for specific funding to test our device degradation. But I can tell you for the OLED, they have very stable performance. People have done systematically measurement on the degradation of OLED. They can last at least 20,000 hours for the OLED, packaged OLED display. So it's on organic materials too. But for the solar PV, we haven't specifically done the measurement on the degradation. But it's still worthwhile in terms of, in the long run, in terms of its real application, we need to do the measurement and test of the degradation.
Guodan, on behalf of their school, I'd like to thank you very much for your talk.
Thank you all.